Welcome back, everyone. So today we are going to be revisiting our two-part series on the linear independence and dependence problem. And last time we figured out that this set of let me make it clear that this set of vectors here, that set of vectors is linear spans R3, because the reason being is that we proved that if you give me any values of x1, x2, and x3, then I'll be able to, any values, so any vector in R3, then I'll be able to give you the value of C3 and C2 and C1. So this means that we can basically, for example, if you give me some vector like negative 2, 3, 4, you plug those into these equations, starting from C3, and then whatever value you get out, that means you have to scale the three vectors by that given coefficients, and then you get vector combinations problem, simplify, and then you should get that vector back. So now today we're going to be actually checking to see if this set of vectors is linearly dependent or independent. Now it should be pretty obvious that this set of vectors is dependent because it spans R3. But what we can check to see is we can actually write this down firstly. It's very similar. What you'll see is that maybe since I've said it now, it should seem very similar to what we. Let me go to our original matrix. So it should be very similar to this original matrix here. Except these values, instead of x1, x2, and x3, they'll be 0. So that's something to keep that's something to note. So actually we don't even have to write this out again. Well, I'll just write it out, just to make it clear. So let me write it. Actually, we don't even need to write it out. What I'll do is I'll just explain it here. So take a look at the set of vectors again. Now this is the one that we converted to reduced row echelon form via Gauss-Jordan elimination. So really what we're doing with linear independence and dependence, since we've already found the equations for that given idea, to prove that that the set of vectors spans R3, since we've done that already, we can see that all we have to do is plug in 0 to our equations. It's really that simple, because I don't know how I can stress this more, because let me look at our equations. So you see, all we have to do is just plug in 0 into these equations, because that's the set of vectors. It's technically still a vector in R3. It's the 0 vector in R3. It's 0. It's the column vector 0, 0, 0. So all we have to do now is plug in 0 into all of these equations. So let's do that. So let's start off with C1. I think I'm actually going to give myself some space, because I don't want to keep going up and down, So this is going to be our new part. I'll use red. Okay. So we start off with C3, as you remember. So we can write this out. So C3 equals negative 95 52.25 over 52.25 times, I don't have to write that dot out, obviously, times 15 times 0, right? because all our values of x are 0 plus 0. So we can just cancel this out, and we're left with 0, since that constant by the, over there multiplied by 0 is just 0 as well. So C3 equals 0. C2, oops. Let's see. This is going to be a very short video because it's pretty self-explanatory. So as we can see, over at this equation here, we can see that we'll obviously get 0 back, because if we substitute 0 for this value here, and 0 for this value here, and 0 for this value here, because C3 was 0, we just figured out that C3 was 0. So we can just do that, and divide that by 1.5, then all you get is 0, of course. So let's just undo that. So we can just write this as 0. It's basic arithmetic, guys. I don't really have to explain much of this. So now we do the exact same thing and work this out. So basically, hold on, did I miss something? C3. Oh, never mind. Wait. I was looking at C3, sorry. I almost messed this up. Anyway, so I'm looking at C1 now. So this equation here. Anyway, so this is now let's plug in for x in C3 and C2. So C3 is 0. Okay, let me make this clear. C3 is 0. C2 is also 0, so that term is 0. So 0 minus, so, and then x1 is going to be 0. So 0 minus 0 times negative 1/4 is just 0. So I'm going to undo all of that. And that's equal to 0. Right? It's that simple. Okay, so now we've just proven that this set of vectors, oh, I didn't even explain why this would work. So now we've just proven that this set of vectors is linearly independent. And you would understand why if you haven't watched my previous video on linear independence, the more in-depth video on it. I did 2 parts of it. Well, basically, just to quickly summarize, if you have some constants C1 times some vectors, it's just going to be a linear combination of vectors. So Cn times Vn. Well, if all of these values of C1, if all values of Ci, hopefully I don't even have to write that, I can just say if Ci, so just any Ci, if, actually I should probably write if all Ci's equal 0, then the set of vectors, just make this as fancy as possible, v1, v2, vn is, I'll abbreviate this, is independent. However, again, I'm not going to write this down, but as we covered in the previous videos, if if that's not, if at least one value of ci is, oh wait, and I forgot to write equals 0 vector. I forgot to write this. So that's supposed to be the 0 vector, bolded 0. So yeah, if the only value of ci satisfies 0, satisfies the equation as 0, if that's the only value that satisfies this equation, then this set of vectors is independent. However, if at least one value is greater than 0, then this set of vectors is actually dependent on each other, because it's pretty trivial, because you can divide, assuming that C1 is the one it's one of them that is one of the constants or the scalars that is not 0, then you could divide both sides. I covered this by C1, and then you minus V1 on both sides, and then so minus V1, and then you multiply everything by -1, and you'll prove this, but I'm not going to cover that. You can revisit my other video. So, hopefully you enjoyed, and let me just revisit this again. This has become a longer video than I expected, but obviously we see that we've just shown that the only value of c that satisfies the equation is 0, so it's independent. So hopefully you enjoyed, and I'll see you in the following videos. Bye.